Hello, good morning. We are going to be presenting leak detection in hydraulic systems, and the team is conformed by Miriam, Leonard, and me, Renata. Improving pumping, developing treatments on the material used, and maintaining the system without leaks is essential to have an adequate piping service. Old and poorly constructed pipes, inadequate corrosion control, poor valve maintenance, and mechanical damage are some of the contributing factors to leaks. Of the many options available for water conservation, leak detection is a logical first step. To combat water loss, methods to detect, locate, and correct leaks are being developed. The following slide shows our results on detecting a leak in a container and determining the impact of it. Our objective is to develop a hydraulic network of water distribution. The system must be able to detect liquid leaks at different points of the hydraulic network from measurements of pressure drops. Some of the considerations we needed to take into account were the essential concepts and formulas. The concepts we used were volumetric flow, that is the volume of fluid passing through a cross-sectional area per unit time, the density, that is the mass of the object compared to its volume, the pressure, that it indicates how much force acts per area, and the capillarity, that is the behavior of the formable interface between two immersible fluid phases. For formulas, we use three main formulas that are the Torricelli, Bernoulli's, and Euler's formula. Then we also needed to have the tanks measurement. We also needed to consider the MATLAB code, and we use the four methods and graphs. The four methods are the middle point, the trapezoid, the right side, and the left side approximations. We also use the calculus programming and physics knowledge. We also needed to use analytic thinking, and lastly but not least important, we use the Tracker software in order to get all of our experimental data. Some of the difficulties we managed to have during the elaboration of this challenge, in the theoretical and methodological issues, we have that the challenge wasn't properly explained. We have uncertainty in calculation amount of volume lost, and we have the wrong methodology to unlead hole in the tank. In the modeling issues, we have that the MATLAB code it was not compatible with our PC. We have a lack of MATLAB code explanation and the difficulties of loading the data to MATLAB.
Some of the basic concepts we use in this challenge, it's Euler method, that it's a numerical tool that helps approximate the values for the solution of differential equations. The Torricelli theorem, that studies the flow of a liquid contained in a container through a small hole under the action of gravity. And the Bernoulli's principle, that is, as the velocity of the fluid flow increases, the pressure exerted by that fluid decreases. And these are the three formulas for the three concepts. For the modeling, we use this code that we first take every single data that we have. For example, the area of the container, the area of the hole, the gravity, the time, and the height. And we use the trapezoid method and the Euler's method. And with this modeling, with this MATLAB code, we graph the experimental method, the velocity versus time, the flow, that is the flow versus time, and the Euler's method, sorry. For the results, we got the position of the leak. The position of the leak is 0.075 meters. And for this, we analyze the graph. And on the breaking point, we got to know which of the position of the leak. Also, we compare it to the height of the container. And the position of the leak is 0.075 meters. We can determine that its location is there due to the fact that analyzing our experimental data, gave us the opportunity to observe that at the starting point, that 0.15 meters, both of the functions seem to start almost with the same inclination. And in a short period of time, the function representing the container with a leak presents a more depth graph. Also, by comparing both of the graphs, it can be observed that at 0.075 meters, the two functions present a breaking point, letting us know that the leak is there. To check our analysis was correct, we compared the analysis with our measurements taken at the beginning of the challenge, where we saw exactly at what height we had placed the hole that represents the leak, and both of the graphs and our measuring match. Then the volume lost by the leak, the volume of the fluid lost by the leak is 0.0793396 meters squared. In order to calculate the volume of the fluid loss, we subtract the areas under the curve of the integral of the function without the leak and with the leak. And it is important to mention that the rate of the change of the volume loss diminishes as the time passes by because the height is less. Therefore, at the brim of the container, the amount of volume lost is the maximum one. And for this, we use the MATLAB code of this. This is the trapezoid method.
So now we're gonna discuss the leak repercussions on the system. First, the loss of energy. The leak Bernoulli principle says that is the fluid does not exchange energy with the environment, it remains constant. The three types of energy are taken into account: hydrostatic, kinetic, and gravitational potential energy. On an increase in fluid velocity, the static pressure or potential energy of the fluid decreases. Taking into account the energies involved on the system, it can be said that there is no loss of energy, since according to the principle of conservation of energy, there is no loss of it. But now it is important to take into account that the leak is generating a change in energy using Bernoulli principle. Energy is always the same. For the impact of the leak in the system, we can say that the leak caused the fluid that is being contained to be lost, creating a waste of this resource. Furthermore, when there is a leak, there is also a loss of pressure, and in order to compensate for this loss, it is necessary to constantly increase the pressure. The increase in pressure worsens leaks and has a negative impact on the environment.
Okay, thank you very much, Renata. So I will tell you about the comparison of the theoretical prototype with the modeling. So in general, you could say there's big differences between the theoretical of our model and the following exercises. So first of all, you have measuring errors in times and length. So for example, if you take a watch, then it's not very exact. And the second, the energy loss due to friction. So so in our thing, there's a quite loss due to friction, and that's not the ideal experiment. Third point is the measurement errors due to vibration. So as a team, we stand near the experiment, and we had a lot of vibration, which changed like the system a little bit. And the fourth point is measuring cup is not an ideal cylinder. As you can see on the right, we had this more the cup, and on the left side you can see the ideal cylinder. So we took the experiment as an ideal cylinder, but actually it wasn't. So as a conclusion, you could say that all entropys of the experiment lead to differences, or you can say errors compared to the theoretical model. Next slide, please. So in conclusion, you could say we have learned the differences in theory and practice. So based on the experimental data, we are able to use a model graph, which Renata and Miriam shows you before, which allows us to find the lead position and the volume loss of the water flow. So there we know the impact was lead by Corshing in our system. And we are also able to practice different the differences between the theoretical principles and also the practice, as I mentioned before. So we could conclude that the lead detection is very important because this way can prevent the loss of waste of the resource that the system contains. So that was our presentation. Thank you very much for listening. And now the last slide is our references. So thank you very much.